What happened in the GPU process?
I guess, yeah. I'm just wondering how. Yeah.
That's
We'll talk about it later.
That's a very interesting thing.
It's essentially within the same channel of communication here. Similar but different to the command buffers, we have ways to have the renderer send bits to the GPU process, be notified when they're decoded, and we make sure they end up in GPU textures so that we can use them in compositing. I go over that afterwards. I know this is going to be a bit of a distraction.
Yeah, okay.
So this is the general architecture that we had 2 years ago, essentially. Okay. So we mentioned threads, and so we're going to talk about what the compositor thread means. So in this incarnation, WebKit runs on the same thread as JavaScript, the main thread in the renderer. So does CC. So CC, which deals with just putting all this into one texture, will issue the GL commands from the main thread. One of the things we wanted to do is to be able to do relatively simple things on a different thread. The relatively simple things are typically scrolling and animations. So things that CC can understand and express in its own language, if you want, restricted language. Once we have this layer, we know we have a page, that's big like this, and we have a layer that maps part of it. We can say, hey, well, we can just change the coordinates, like the view of this layer inside of the content, and we can do that and just re-render a frame. We don't need to talk to WebKit to be able to do that. The problem is, if WebKit is busy, because JavaScript is busy, are we doing layout, are we doing something that's very expensive, we could do this very fast, but we just don't get a chance to do it. So it can add jank. Just because JavaScript is busy, you cannot scroll the page, it sucks. So we added the compositor thread. The idea of the compositor thread is essentially, so CC maintains a layer tree. We have a root layer, and then you have, in this case, you would have what we call a content layer. Content layer. And then we'd have a texture layer. And we'd have another content layer. This would be the root layer, this would be the WebGL, this would be the image. Then we can have different combinations. We can have hierarchies where you have more layers, like if we went to iframes or like different hierarchies. It doesn't really matter. We can have an entire tree. This is maintained on the main thread. I think the compositor thread is saying basically we're going to duplicate this entire layer tree onto another thread. So we have a copy of this. And that copy we can operate on to do the simple things we talked about. Changing the scroll offset, animating some transformation metrics, basically. Those few things that we know how to do because we understand enough of the world to be able to do it. So basically, we have the layer tree, and we have in CC what we call the layer impole tree, which is very bad naming, but that's what it is. For every layer on this side, we're going to create the evil twin of it, the impole version. So we have a content layer, we have a content layer impole. We have a texture layer, we have a texture layer impole. Content layer impole. And they match one-to-one, texture layer impole. And this is, so this essentially lives on the compositor thread, this lives on the main thread. So what happens is WebKit will modify this tree, and then we have what we call the commit phase. The commit phase is basically taking this tree, synchronizing it with the import tree, and then letting this thread run. Since it runs on another thread, it will do its own scheduling and everything, and say basically, oh, I got a commit, something changed, I'm gonna draw a frame. You can do that without talking to the main thread, which means that if the main thread is blocked in JavaScript, we can say scroll, we update on the import tree the scroll offset here, and we say, oh, well, we have all these textures, we're gonna move it there, and basically everything we can draw a new frame, without having to wait for JavaScript. So that's how we get to smooth scrolling even with janky stuff.
So a scroll event is fed both, is put into the queue into JavaScript and then passed to the compositor
If we were
thread?
doing that, it'd still be janky because we would have to JavaScript to process the event before getting on CC. So what we do instead is we capture, so the events come here, from the browser to the renderer as a message. We capture that message on the IO thread and we send it to the CC thread first, the compositor thread. Then the compositor thread says, oh, this is a scroll event, I know what to do with it. I know that we add some meta information here, metadata, that says, this content layer is scrollable. Like, there's nothing that at the WebKit side will want to hook into the scroll event that touches any of these. So because of that, we know we can scroll it on this side. So we're gonna scroll that and then send the event to the main thread.
Okay. How about this case where the page has this little div or layer that sticks to the bottom, like you scroll and...
Fixed position divs, the vein.
It's the worst thing that ever happened to rendering on the web. We can encode that information in the compositor's layer tree because there's nothing kind of inherent, there's nothing, what used to be hard about that is that if you had kind of like a fixed position element all the way down the side and all the way across the top of the screen and you shift it up a little bit, we need to repaint kind of everything because we would union the damage rect, right? Instead, we can have a layer for that fixed position element on the side, a layer for the fixed position element on the top, and a layer for everything else. And then we can update the positions of these things independently, right? Because in the like draw phase, where the compositor actually mashes all these images together, the offsets can change.
So I guess it goes a little bit into this, how WebKit decides to make layers.
Yeah.
As long as it's in a separate layer, so here, we have one layer for what's in the back, and then, you have a butter bar at the top or something. If we know that we should promote it, and we do promote it into a layer, then we're good, because we can paint with this thing once, send it to the import thread, same on here, paint enough that we can scroll, and we can decide, hey, scrolling, we can still just scroll this. The problem is, if we, for some reason, could not do that, and it used to be the case that we would not promote, and I'm not the expert on this, but there's lots of different reasons why we could or could not do it. CSS is very complicated.
Yeah, we've actually thought through at this point all of the CSS spec problems, and on platforms that have higher device pixel ratios, we do this. Where we don't do it is on standard resolution displays, which includes most of the desktop population. And the reason is that any text on any one of the layers that isn't the root, that isn't on an opaque background, so like each of these layers is painted individually now, and if the layer's background is transparent, but there's text on it, we lose the subpixel anti-aliasing, which you can get away with on this guy, but you cannot on most Windows machines.
So if for some reason
Sucks.
we decide not to promote this layer, then we're in the situation where scrolling is more than just shifting pixels around. We actually have to
It's actually
go
much
back
worse
to
than it used to be. Yeah.
It's very bad because we're like, oh yeah, we can scroll, and like, well, crap, this layer, we have to go back to the main thread to paint it.
And
So
not
instead
just
of-
a little bit, but the whole thing, and we have to re-upload it to the
Right.
GPU, which is like way more overhead.
So, so that's what's happening. Still here, in this infrastructure,
So is the entire purpose of threaded compositing to allow smooth scrolling?
and smooth animations, essentially.
Yep. It's infeasible to scroll smoothly on low-powered touch devices without this.
But there's not any other like side benefits or any other substantial side benefits?
There are some, like, the way we do the scheduling is different and we have more control on the scheduling on the thread because we're not dependent on what JavaScript needs.
Having a dedicated thread that we know won't jank,
Yeah.
aside from the renderer's main thread, is also very useful as we try to get more crap off the main thread. So in way down the line in Antoine's evolution, maybe we'll get to nipple-side painting where we try to move raster off the main thread, and we let the compositor thread control yet another thread that's doing the rasterization.
Many other threads.
Because unlike the renderer main thread, we're guaranteed that the CC thread will actually run once
But
it's
yes,
framed.
So
the
in-
main purpose of this is to have smooth scrolling
Yeah.
and
And animation.
animation.
So impulse-side painting is a renderer only technology, or
Actually,
Well,
no,
we haven't
but
even
today-
gotten to browser compositors yet, but.
all right? Let's keep going.
And I was gonna stop here for the renderer side and touch this afterwards, just so that finally we get to Aura.
Yeah, I think that's
Yeah,
the
yeah,
right thing to
yeah.
do.
Totally.
Okay, so so this is what we have. Then came Chrome OS. The desire to change.
One second. So 5 more minutes, and we'll take a small break.
Yeah. Or you want to take a break now?
Well, in 5 minutes. So an hour block.
So, we wanted to redo the UI on Chrome OS. It used to be done with a traditional X11 window manager type thing. And it was completely outside of Chrome. The UI people could not really iterate on it because we didn't have any of the facilities in Chrome, and the architecture was kind of crappy and stuff. We decided that the route forward was to, instead of trying to have two separate things that didn't talk very well to each other, is to move all the desktop UI management and everything inside of the browser process here. So talking directly to the Chrome UI, so that we have one good place to do all the communication between what's really the browser window versus what's the system. It's sort of blurred more and more, as you can see in the current UI, between the system notifications and the apps list and so on. It gets fuzzy very fast. And UI people wanted to iterate on the UI, so we decided, hey, let's create a UI widget here that we can GPU accelerate. And this will need a compositor, because the sort of UIs that we wanted to do looked, not exactly, but somewhat similar to what we do on the web. Like, you have layers that may be transparent, animated, and so on, and we wanted this to be smooth and fast and everything. So we decided, hey, what if we took the compositor that we have created and expose it in the browser, so that we can create layers, we can put animations on them, and everything will be smooth and stuff. That's essentially what Aura is. So Aura is basically saying, let's add CC here. Let's put how should I create that? Something that looks like Windows on top of this. That's Aura. I think it mostly is meant to replace Win32 in spirit, at least. And reuse the views widget set that we have for Windows on top of this. and then, the regular UI. So basically what we have here is Aura has this concept of windows that are backed by layers. And views, you have views inside of those windows. They may have their own layers as well, but mostly, we deal at Aura window level. These directly look like a content layer from the CC point of view. So what's happening here is basically we create the UI in terms of these Aura windows. We create our hierarchy, we create our parenting, our event processing and everything. And Aura is basically what will produce these pixels that will go into tiles. And that's essentially it. So at the very beginning, because we were talking to the GPU from the browser, we were talking to it directly. It quickly caused big performance problems because of how we want to present the render frame inside the browser. The idea is we want to composite it with the rest of the world. So you have to take whatever is produced by the renderer into a texture so that you can put it inside of a texture layer inside of CC in the browser. We went through several iterations of this, but at the beginning we were doing the same thing we do on X. We have an X window that backs the renderer, and then we try to grab there's APIs to do that, put them into textures. It was very slow, it was horrible, it was racy, and it was terrible. So what we decided to do instead is have CC in the browser talk to the GPU process as well. What this gave us is we can directly at the OpenGL level share textures. It's something that can do generally cross-process, but inside the same process you can share textures between all these different contexts. So where we ended up is the renderer, instead of rendering to an X window, and I'm talking about X because Chrome OS is in X, so studied in X. The renderer, instead of rendering to an X window, renders to a GPU texture. We pass that here with this message here. We pass that texture to the browser that puts it into the layer that represents the renderer. And we kick the compositor inside of the browser that will then composite the entire browser to the GPU that will then go to the X window. Yep.
Why couldn't we just have the browser send its UI layer tree to the GPU process and have the renderer send it to the GPU process, and then just do it directly there, and then that would save one trip, right?
So when you say sending the UI tree, it's actually one of the things we explored.
Or not, I mean, it doesn't have to be a tree, right? Because it's always a rectangular area, so you could have no, I guess you would have sent a tree, yeah. Yeah.
So it's sort of where we went through different designs. But so currently this is what we have evolved like this to some extent, and I'll get over how we make this better without needing these round trips. But in a nutshell, the way we feed the pixels into those layers is very synchronous. So if the layer tree was in the GPU, we would need, anytime we need to fill in any of those, because the CC decides, oh, I know what's visible, so I know which of these tiles need to be filled in. It would have to go do a round trip to the browser, because the browser is the one that knows what to put in those layers. That's what can access the profile to see your name. That's what accesses the network status to see to do the network bar and so on. So you would need anyway these round trips, and we decided as an architecture that we didn't want that. So I mean, keep in mind that this round trip itself is not really a problem. This round trip, like sending a message from here to here, is less than a few microseconds. The UI thread here is responsive. It's never blocking. It's true on Chrome OS. if it's not, you have other problems anyway.
We have other problems anyway.
So, in practice, the fact that we have a round trip here is not the problem. What can be a problem, and that's where we get into the Aura Compositor issue, is that it does add another compositing pass. So basically the idea here is we take all this layer tree here, squash it into one texture, take that texture, squash it into another texture, or the final frame buffer. This squashing operation basically has to at least read every pixel here once and write it once. And then same for this one. So the Aura Compositor, which we'll go over maybe afterwards, is an attempt to save this.
When you say read every pixel once and write every pixel once, is that the same as like a mem copy?
Essentially,
Okay, it's not anything more. It's not like.
It's in the GPU, right?
it's on the GPU. On low-end machines where you're very often limited by the memory bandwidth, it matters.
Yeah.
Depending on your resolution. Do you want to take a pause now?
Yeah.
Yeah.